The first way we could implement a simple table is with using an unordered list. So this is maybe our simplest possible choice. It's also maybe going to be our slowest choice. In the end, we're going to end up with a nice table that shows, the different performance from these different approaches. Again, right, we're going to go out, kind of walk through these and try to figure out, what is the best we can possibly do. So our first thought here, right, is to start with a list. Lists are nice because they're easy to maintain. If I want to add something, I can just throw it in the beginning of the list, right? I don't need to worry about arrays, resize, I don't need to worry about all that stuff. It just works, okay? So lists are very simple to use, at least if they're unordered. So let's start by looking on the right-hand side of this trace, right? So this is a trace of a bunch of put operations. So here I'm doing basically all these different puts. So initially I do put of s, right, with 0. That means I get a list inside, right, that has s and 0. Then I do a push, put with e and 1. That means I basically add something, right, add to the front. Do another one, adds to the front. I keep on adding elements, adding elements, adding elements. So these red ones here are basically me adding new stuff. Okay, it's unordered, right? So it's easy to add. Just throw something in there. So my put operations are looking pretty good, right? Put is probably something that's super simple to implement with lists, right? It's going to be O of one time. I'm just adding a new thing, right? For some cases, I shouldn't have said that. So it's not going to be O of one. It's O of one to add it, but we need to do some work before we add it. So yeah, here, right, you're just kind of adding things to the list. Then we do, this is a little bit more interesting here, E of 6. E already exists in my list, so I need to go to that location. I basically need to update it. So here, my E over here, right? See how this 6 has been circled? That's the notation here in the graphic for I updated something that was already there. Originally E was 1, now it's 6 because I did a new put, right? As I do puts, I should be updating the value that's associated with that particular key, right? I can't have, keys can only be associated with one value, so if I do a put on a key and I give it a new value, well, I need to update the value or replace the value that's already there. Otherwise, things just get confusing. So that one's been updated in place. The rest of the trace here does the same thing, right? So I have, sometimes I'm adding things to the front of the array because they're completely, in front of the list because they're completely new. Sometimes I'm replacing different elements in there because they already exist, right? I'm just updating what is that value they have associated with them. So I do all that, right? So all that looks fine. This is our rough mechanism for doing puts. And if I do gets, well, gets aren't going to change the structure of my list, right? I don't want that to be destructive. If I do a get, basically I have to look at my list and I have to search along it, okay? So yeah, let's actually talk about those searches though in a little bit more detail. So here are my questions in the slides, and I'll work through these with you guys. If you have an idea, right, you might want to, actually, if you have a second, basically, stop the video, think about these first 3 things here, right? Unsuccessful search, successful search, insert. How many elements do you need to roughly touch there? So think about that for 1 second, and then I'll work them out with you guys. All right, so unsuccessful search. Unsuccessful search basically means I'm going to go look for a key that's not in my list. Well, if I'm looking for a key that's not on my list, that means that I'm going to basically, start looking here. It's not there, look there, it's not there, look there, not there, look there. Keep on, and all of a sudden, I've touched everything in that list. Say the list has n elements, that means that I had to look at n different things. So that's a really costly operation. I had to go through there and find, right, I had to go through there, right, and basically, look at all n elements, right? So this is the worst case. What about the successful case? Successful case, so successful search in the worst case. Well, what is the worst place it could possibly be? The end of the list, okay? So in that case, it's actually going to be n as well, because I had to, go through here and touch each of these, right, on the way to the end. Still n elements, right? So I had to look at n things. I guess technically if we want to be super precise, the top one is like n plus 1, and the bottom one is n, right? We had to go all the way. All right, insert. Insert for worst case. Insert for worst case basically means that we had to go through there and we wanted to insert some value, and we looked through there and we just couldn't find it, right? So it's the same thing basically as an unsuccessful search, because we need to basically, when we do an insert, we need to do a search for if it's already there, because it's already there, we need to update it. So an unsuccessful search is the worst case there, right? It's that's what we'd have, right? If we did an insert and it wasn't already available in that list. So it'll be an n plus 1 again, because again we have to just go to the end. So these are looking a little bit bad, right? These are all linear time. So I basically have n for the number of comparisons I need in worst case. More interesting question is, how many comparisons are needed on average? Okay, average is more realistic. So how many comparisons are needed on average, right, for a successful search? Okay, so this one, right, more useful. The answer here, well, okay, so let's say we're searching for an element, right? Normally the sequence of operations, right, would be to start here, search, 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 right? We keep on doing that. But that's just for the case of it being at the very end. I had to go look for everything. But the thing is, it's not always going to be at the very end, right? So sometimes it could be here, sometimes it could be here. Sometimes it could be here, sometimes it could be here. What do I do with that? Well, what I somehow realized, right, is that by the time I get through half of the array, I have basically a good chance of having, seen it, right? Because there's basically a 50% chance, right, that I see it on this half versus I see it on this half, right? So if I get through basically half of it, right, then I have kind of a chance that I've seen it. So on average, what I end up with is a factor of 1/2 in front of it. So it's 1/2 n. So on average, I'm going to need to only see half of the array, right, before I see what I want, before I get to, the element that I need to, right? Because there's a chance that sometimes it'll occur here, right? And then sometimes it occurs there, right? So it's like, imagine you have 0 compares needed over here versus n compares over here. What's the average of those? The average of those is n over 2. Well, it's 0 plus n over 2, which is n over 2. And you can imagine, right, if you do this again, right, for this, the math ends up being just n over 2, n over 2, n over 2, right? Because sometimes you'll do it faster, sometimes you'll do it slower. So this ends up being our average time. So yeah, kind of nice, kind of nice. Yeah, so it's basically the time to access each element divided by n, right? So it's like the time you potentially have for here, for here, for here, for here, for here. But yeah, I think the kind of the easy way to think of it is, sometimes you'll see at the beginning, sometimes you'll see at the end, and they basically cancel out, and when you average them, you get that 1/2 factor. So yeah, that's what we have. So we have basically n for our worst cases, and then 1/2 n for our average search case. So this is what it's looking like right now. This is basically what we have to beat. What we have to beat is linear time for all of our operations. All right, so the code for this, we're not going to really talk about on the slides. If you want, you can go look at the book's website. The source code will be available. We won't really go into it, though, because, again, this is kind of our slowest approach. We can do a little bit better. And that's what we'll do in our next video, in which we'll start talking about the array implementation of this data structure.